Hey guys, today we're going to be doing a laboratory exercise where we're going to attempt to use the gas laws in order to calculate the molar mass of a gas. In this case, we're going to be using the gas butane, and what we're going to do is through the processes of this lab, try to figure out what is its molar mass. So let's go ahead and get started with the procedure. Let's talk procedure. So in this lab, it's fairly straightforward, not a whole lot of things we need to use. We're going to use a eudiometer to collect and measure the volume of gas that is going to be released. Eudiometers are great for this because they have a closed top. They're demarked with measurements just like a burette would be, and they've got a nice open bottom that allows us to actually collect and trap the gas. We're going to use a large beaker. You might also use a bucket for this, but it just needs to be big enough for your hand to be able to fit in and then release the actual gas itself. It also needs to be deep enough to be able to measure the volume of the eudiometer. We're going to talk about how to do that in a little bit here. We've got a butane lighter. The butane lighter is containing the butane that we are going to have as vapor. Butane is a highly volatile chemical. What that means is it vaporizes very quickly and easily at low temperatures. This is good for us because we need to make sure it vaporizes quickly so that we can obviously do this in a short amount of time. We're going to use a thermometer to measure the temperature of the room. And we've got a gas pressure sensor here to be able to measure the barometric pressure of the room. All right, I'm doing that using one of my lab quests here. So let's talk about what we need to do. All of this lab is predicated on one thing, the butane. So we need to be able to get a precise measurement of butane, and we're going to be looking for the grams of butane that are released. Because in the end, we need to figure out what is the amount of butane released, and grams is the best way to do that. So the way we're going to do this is because the lighter is going to end up in the water. Right? That's how we're going to release the butane into the eudiometer. Because the lighter is going to end up in the water, what we're going to do first is we're going to dip the butane in the water. We're going to hold it there for a couple seconds, kind of roll it around. Now what that's going to do is that's going to get the butane lighter wet. When it's wet, it adds a little bit of mass. The problem is if we measured it dry now and then wet later, we'd have a source of error. So we don't want that. We're going to get it a little bit wet, and then what we're going to do is I'm going to take it out, I'm going to shake it off. All right, I'm going to keep in mind about how hard I'm shaking, how much I'm shaking. I'm going to dry it off as well, all right? Because here's the thing, is it going to be perfectly dry at this point? No, but we also don't necessarily want it to be perfectly dry. I'm now going to take this lighter, and I'm going to place it on a zeroed balance. That's my initial value for mass. So I've got an initial value for mass now. And in my initial value for mass, I'm going to then take this and I'm going to start the experiment. Again, keep in mind how wet the lighter was when you took that mass. In order to do the experiment, I'm going to start by taking my eudiometer and submerging it into water. But it's filled with air. That's not going to work. So what I need to do is I need to quickly fill the eudiometer all the way to the top with water. Now my eudiometer is filled all the way to the top with water. The reason I want this is because what I'm going to do is I'm going to invert the eudiometer, and when I invert it, I don't want there to be any gas in this at all. The only gas I want is going to be the butane from the lighter. So this is going to take some skill. You're going to plug the eudiometer, you're going to invert it, making sure you're under the water, and then you're going to release. As you can see, no bubbles traveled up the eudiometer. That means I did a good job. I can then use a burette clamp here to be able to hold the eudiometer in place. Now, as long as the top of the eudiometer, so the open end of the eudiometer, stays under the water level, I'm going to be okay. What I want to do is try to get it as close to the water level as possible. It's going to give me more room to get underneath it. So I'm going to raise the eudiometer a bit until I get close to the water level. Then what I'm going to do is with my already measured lighter, I'm going to take it and I'm going to undo or open the top. So this would be like if I was to strike it, but without striking. I don't want to burn anything. I just want to release the gas. So you can do this very quickly. You're going to take it, you're going to submerge it underwater, and you're going to release the gas. You're going to see bubbles coming up. You want every bubble to end up in the eudiometer. You don't want any bubbles escaping out into the beaker itself. If you see bubbles into the beaker, source of error. So I'm going to do this until I reach a volume. The volume you end up with is going to be somewhat dictated by the actual measuring device you have. You might have a 50 milliliter eudiometer. You might have a 100 milliliter eudiometer. You might have a bucket or a beaker. The key here is whatever volume we add to, we need to be able to take that water level and get it even to the water level in the beaker. So what I'm going to do now is I'm going to lower this back down for a moment and see at what volume do I have to fill this to in order for my water levels to be equal. In this case, it's going to be just shy of 100 milliliters, but yours might be a little bit different. So now what I'm going to do, I'm going to fill my eudiometer with butane. All right, now I have added the gas to the eudiometer so that I know I'm going to be able to measure the volume. Because remember, I need the water level in the eudiometer to match the water level in the beaker. We're going to talk about why that is in a second. But first thing I need to do before anything else happens, I need to get my actual lighter here. I need to dry it exactly like I did beforehand. So I'm going to shake it off, shake it off, shake it off a little bit. Take my towels that I was using earlier. I'm going to try to dry it to the exact same degree I had dried it earlier. And then I'm going to measure the mass. That is my final mass. The difference between my initial and my final, in theory, should be just the mass of the butane that is now in my eudiometer. I need to figure out the volume of the eudiometer now. And so what I'm going to do is I'm going to take my eudiometer, I'm going to lower it until I see that the gas inside is at the same level as the water level outside. It's going to require me to get down and take a measurement. Okay, perfect. Now, once this is the case, that tells me two things. First thing it tells me is that the pressure inside of this eudiometer, that's the force of the gas pushing down on the liquid inside of the eudiometer, is going to be equal to the atmospheric pressure around the eudiometer also pushing down. All right, so there's two forces, one pushing down inside of the eudiometer and one pushing down on the gas around the eudiometer. Once the water levels are equal, the pressures are equal. So the thing it tells me is the fact that I can now look at my pressure sensor, and that is now the pressure of the gas inside of the eudiometer. The second thing I have to be aware of here, it's not just butane in this eudiometer. You want to think it is initially because that's what we just added to it. But in any gas law problem where we're collecting over water, you also have to account for another variable. This would be the variable that is called water vapor pressure. Water vapor is going to naturally vaporize as we are going to be collecting the gas. So inside of this eudiometer is not just butane, it's butane and water vapor, and we have to account for that. The nice thing is, the vapor pressure of water is constant at any temperature. So once we measure the temperature, what we're going to be able to do is then look at our reference guide in our book to be able to determine what is the water vapor pressure at that temperature. Okay, so you're going to need to be able to do that, and in doing so, we can then say, well, if some of the pressure in here is the water, the rest of it is the butane. So in terms of technique, it's a fairly straightforward lab. In terms of error, however, there are a lot of sources. All right, so let's go ahead and now talk about what data we collected, and then also how the sources of error might show themselves throughout the process. So now that we've collected our data and I've taken you through the procedure, let's talk about kind of how we're going to use it. Remember, with the actual lighter, we collected both the initial mass of the lighter, that was slightly wet, and the final mass of the lighter, that was slightly wet. The difference between these two represents the mass of the butane that left the lighter. Then we collected the atmospheric pressure. Remember, in order for the atmospheric pressure to equal the pressure of the gas inside of the eudiometer, we needed to make sure that the water levels were equal. Once they were, the pressure outside pushing down on the water and the pressure inside pushing down on the water were equal. So the atmospheric pressure, again, is the barometric pressure of the room around us, which we collected. The temperature is going to be that of the room around us, right? Remember, we want to leave the water in the beaker so that it comes to the same temperature as the air around us. All right, so we're going to measure the temperature of the air. That's going to be the temperature of the gas. And finally, the volume of the gas that is collected. So the volume of gas collected, we controlled, right? That was our variable that we were able to control. We stopped releasing the gas into the udiometer once it reached the volume we wanted. So that's our data. Now what we need to do is figure out how to plug it in. What do we do? One additional thing we need to make sure of is that our atmospheric pressure that we're recording is understood to be not just the pressure of the butane in that udiometer. Remember, anytime we're collecting any gas over water, we are collecting the gas, but also water vapor. Water vapor pressure is a must in terms of your accounting for. So what we need to do is we need to take the atmospheric pressure, subtract the water vapor pressure, and that's going to be the pressure of the butane in the actual udiometer. So the pressure of butane, again, is equal to the atmospheric pressure minus the pressure of our water vapor. Now that we have all of our numbers, we're going to go ahead and plug into our ideal gas law. Remember, ideal gas law, PV equals nRT. All right? So we need to figure out the molar mass of butane. Well, molar mass is grams per mole. So if I'm looking for grams per mole, I have the mass of butane in grams, which means I just need to find the number of moles. Well, the number of moles is a component of our ideal gas law. PV equals nRT. Moles equals N. So let's go ahead and write our ideal gas law and figure out where each of these things is going to go. Remember, pressure here needs to be the pressure of butane. And the pressure of butane in this situation is going to be the atmospheric pressure minus the partial pressure of water, or the vapor pressure of water, which is a constant at any temperature. You're going to look that up in your textbook to be able to figure out what the partial pressure of water is at the temperature we were collecting it. So that's the pressure of butane. The volume is going to be the volume of the gas collected. Okay? N is going to represent the number of moles of butane. That's what we're looking for. R is our gas constant. R is going to determine what value of R you're going to use is determined based on the pressure units that you're using. So if it's atmospheres or kilopascals or torr or millimeters of mercury, the R value is going to change. So just make sure you're using the correct R. And T, remember, temperature always must be in Kelvin. So you're going to plug in these values, and you're going to find the number of moles of butane. Once you know the number of moles of butane, again, molar mass, grams per mole, mass of butane in grams, moles of butane. So what we need to do, take the mass divided by the number of moles, and that is going to give us our experimentally determined molar mass of butane. So once we get our experimental value, the odds of it being precisely what is expected are very small. Let's talk about the types of error that we might see in this process. So remember, types of error include measured values, right? Things that we are looking for, looking at, not calculated values. Calculated values are not accounted for in terms of error, just measured values. So what are we measuring? Well, we're measuring the initial mass of our lighter, the final mass of our lighter, right? We're reading the atmospheric pressure, we're measuring the temperature, and we're collecting a certain volume of our gas. In other words, these are our measured values. So these are the ones that could see sources of error. Now, you have to think about how these would affect our calculated value. Remember, we used pressure, volume, and temperature to measure the number of moles. We used the masses of the lighter to measure the number of grams. So any error affecting the mass is going to affect the gram aspect of the equation, and any value affecting the number of moles, like pressure, volume, or temperature, is going to affect only the moles component of your equation. So keeping that in mind, because molar mass is grams per mole, if the error causes the measured grams to be greater, that's going to increase your molar mass calculation. Why? Because if it's grams per mole, your numerator gets larger, your denominator stays the same, And therefore, what we end up with is a greater molar mass. So that'd be a positive experimental error. Conversely, if anything is going to make the mass less, again, this is going to be the mass of butane. If you make it less, that's going to create negative error because now your molar mass that you calculate is going to be less than you would have expected it to be. You have to be able to account for these sources of error. So things that could create error. What if your lighter wasn't as wet as it was to begin with? So your final mass of lighter, there's more water on it. Well, more water does what? Adds a little mass. Adding a little mass here does what to your total mass of butane? Well, it means less mass would have left because all of a sudden your lighter is not as light as it should have been. All right, so the mass might have gone up there. You have to think about this in each of these different contexts. So be careful, understand what you're measuring, understand what you're calculating, and be able to connect the two to determine which direction the error is going to push your resulting data. So that wraps up today's video. Today we went through the procedure for the molar mass of butane lab, and so the objective, remember, for this lab is to figure out what is the molar mass of butane using our ideal gas law, and also being able to take understandings of different sources of errors and seeing how they might manipulate our data, either to create error in one direction or the other. I'd like to thank Jonathan Wessler and Will Picard for writing, filming, and editing this video. I'd like to thank you guys for watching it, and I'll see you in the next one.